come to get bottled water?
I have it right here.
Oh, you have? Okay.
Friends,
It's my great pleasure to introduce Professor Bruce Berndt from University of Illinois at Urbana-Champaign, USA. He's one of the world's foremost authorities on the work of Srinivas Ramanujan. Professor Berndt received his bachelor's from Albion College in Michigan in 1961 with majors in both mathematics and physics. He then went to University of Wisconsin, where he obtained his Ph.D. in 1966 under the supervision of J.R. Smart. After an assistant lectureship at University of Glasgow for 1 year, he joined the faculty of University of Illinois at Urbana-Champaign in 1967. After 52 years of teaching and research at the University of Illinois, he retired this May 2019. He has supervised the doctoral dissertations of 37 students and has mentored 10 postdocs. He is a former Guggenheim Fellow, and he received the Steele Prize for Mathematical Exposition by the American Mathematical Society in 1996. He has written 14 books, including 5 volumes on Ramanujan's notebooks and another 5 on Ramanujan's lost notebook, joint with George Andrews. Today, he will be talking on his association with Ramanujan's work since 1974. Over to you, Professor.
Thank you. Yeah, let me begin by giving you an outline of what I plan to speak on. So for the first part, I will say a little bit about Ramanujan's life, and then I will tell about Ramanujan's notebooks, and then thirdly, I'll tell you autobiographically how I became interested in Ramanujan's notebooks. And then fourthly, I'll tell you how the lost notebook was discovered, and then give you some examples from the lost notebook. And then lastly, I'll ask a few questions about Ramanujan's manuscripts, in particular, maybe some missing manuscripts. So that's an outline of what I plan to speak on. So I usually begin any lecture on Ramanujan's work with a photograph, and I will actually begin with all 4 photographs that we have of Ramanujan. So this is the most famous photograph. It's his passport photograph. These are, trying to see, oh, here we are. So these are stamps, passport stamps. And it looks like he has a suit coat on, but in fact, this is his bathrobe. And these are actually his pajamas. So he was too ill to have come to the photographer to have his picture taken for the passport. The photographer had to come to the nursing home where he was, and this is that picture. So he usually does not look like this, and the reason is because he is much thinner after the illnesses that he was suffering from in the last few years. So in the next photograph, you will see that here he is. He has a much fuller face and much heavier than he was in the previous photograph. So here, Ramanujan received, he was made a fellow of the Royal Society. So this picture was taken about a year before he returned to India. So about February of 1918. So we know what the names are for the other people who were made fellows of the Royal Society at that time, but we can't make a one-to-one correspondence. So in other words, all we know for sure in this picture is where is Ramanujan's identity. Okay, in this photograph, again, you can see that Ramanujan is much heavier than he was in the passport photo. And this was taken, we think, in about 1917. So let me identify these people in the photograph for you. So behind Ramanujan, this is Sattler Sundara Surya Narayanan. So he was a philosopher at the University of Madras for his entire academic career. He actually got his master's degree at Oxford. In those days, they didn't really give a Ph.D. The master's degree was the highest degree that was earned. Okay, then this person here, this Kayananda Rao, he was a student of Hardy and returned to India, was actually a very well-known mathematician. He did work in analysis. And then this person is Taneti Surya Narayana. His stay at Cambridge almost coincided exactly with Ramanujan's stay, and he also was a mathematician. And then lastly, this fellow here is Adi Narayana Chetty. He actually is a little bit older than the other people in the photograph and is a native of Kumbakonam, Ramanujan's hometown. And he was active with Gandhi in the independence movement. And then the last photograph that we have, probably taken at the same sitting as the previous photograph, is just Ramanujan alone in the chair. It looks like it might have been excised from the previous photograph, but there are differences, and this really is a photograph that is not excised. So these are the only 4 photographs that we have, all, as you can see, taken in England. Yeah. Okay, so now let me say a little bit about Ramanujan's life. He was born in Erode, in the home of his maternal grandmother, and then after a few months, his mother returned with him to Kumbakonam. I had the privilege of actually seeing Ramanujan's home in 1985. So it was a very thrilling experience for me to see the home as Ramanujan probably saw the home when he lived here. So if you, this is in the porch area behind the bamboo curtain. The only way you can see that this was the home of India's most famous mathematician is that the family living in the home had taken a photograph of Ramanujan from a local newspaper, and they had taped it above the entrance to their home. Now, this is a picture of the children and the father inside the home. The person talking with him is our Balasubramanian. He was accompanied me as I went to Kumbakonam. And he was with the Institute of Mathematics in Madras for many years. Okay, Ramanujan, as a schoolboy, worked on a slate, and this is actually the slate on which he worked. So in those days, paper was expensive, so students worked on a slate and did all of their work. So Ramanujan worked on the slate for many years. So I'll tell you in a few minutes why we actually have the slate. So it's in the family of S. Narayana Iyer, whom I will say a few words about in just a few minutes. So this is his grandson with the slate. He has now passed away, but his son now has the slate. And here is Srikanth Narayanan. This person to his right is not his son. Okay, we all have our favorite pictures of ourselves, and this is my favorite picture. With my wife, our wedding picture is our favorite picture, so this is my second favorite picture of myself, and holding the slate. So again, this is a very thrilling experience for me to hold Ramanujan's slate. So Ramanujan started to record his results in notebooks at about, we think, the age of 16 when he entered the Government College of Kumbakonam. Up until that time, we only know 2 books that he studied from. One was Loney's Plane Trigonometry, and this has much more in it than the title indicates. In particular, there's quite a bit of calculus in the book, including infinite series. And then at the age of 15, he borrowed from the Government College Library Carr's Synopsis of Pure and Applied Mathematics. This is a list of between 4,000 and 5,000 theorems with hardly any proofs, just some sketches that Carr used to tutor students in passing exams in London and Cambridge. So we think he recorded his results in notebooks for about 10 years, up until he left for England. So the notebooks are now at the library at the University of Madras, and this is the second, and it's the main notebook. It's a revision of the first, but there are a lot of results in the first notebook which are not in the second. And the third one is quite short. It's not as long as it looks here. There are really only 33 pages that are blank in the notebook. Okay, I saw these notebooks for the first time in 1985. So I took a picture of a couple pages here of the notebooks, and you can see that my flash bulb is reflecting off of the page. Maybe some of you don't know that in the olden days, we didn't have iPhones with nice facilities for taking pictures. We had to use flash bulbs on our cameras. And it's reflecting because the pages were laminated. It was found that insects were destroying some of the notebook pages, and so they laminated actually the pages, and this is why you see a reflection off of my camera flash bulb. Ramanujan married in 1909, I'll get that date straight, and he was encouraged to find a job, and so in 1910 he moved to Madras with his mother and with his wife. So for about 15 months he was supported by mathematician R. Ramachandra Rao, who was fairly wealthy, but Ramanujan didn't like being supported without actually doing a job. So he applied at the Madras Port Trust office for a job as a clerk. And the chief accountant at the Madras Port Trust office was S. Narayana Iyer. And he actually was one of the best mathematicians in India at that time. So he encouraged Ramanujan to write English mathematicians about his work. So he first wrote M.J.M. Hill, who was a professor at the University of London, and he replied, but it was clear that he didn't really understand what Ramanujan was trying to communicate to him. And then he wrote E.W. Hobson and H.F. Baker at Cambridge, but apparently they never replied to his letter. So then, fourthly, he wrote the famous English mathematician G.H. Hardy. And in this letter, he sent Hardy 60 of his theorems. So first of all, Hardy sort of dismissed the letter. Famous mathematicians often get letters from those who want to show that they know a lot of mathematics. But that evening, he and J.E. Littlewood, another famous Cambridge mathematician, went over the letter and saw that this was really the great work of an excellent mathematician. So Hardy wrote to Ramanujan encouraging him to come to Cambridge. Ramanujan didn't respond to that invitation. He wrote Hardy another letter with another 60 theorems in it. In particular, his parents were against Ramanujan, their son, going to England. And so then, after the second letter of Hardy to Ramanujan, which he again encouraged Ramanujan to come to England, his mother in particular gave her permission so that her son could go to England. Yeah. So he left in March of 1914 for England, and before going to England, he traded slates with S. Narayana Iyer. So trading slates, at least at that time, was a sign of respect and admiration. So indeed, Ramanujan had great respect and admiration for S. Narayana Iyer, who hired him. And in fact, the two often did mathematics together in the evening hours after their work at the Madras Port Trust office was finished. Yeah. So it's in his family that the slate now resides. So here is a photograph of Hardy. This is a nice photograph, but I don't like it for one reason. He's smoking a cigarette here, and I don't want to advocate smoking cigarettes in my talks. So for the next 5 years, Ramanujan became quite famous for the work that he did. with much of it with Hardy. However, he became ill shortly thereafter, after arriving in England. So you see here in this letter that he wrote to his friend Vinayaka Rao in Madras, already in March of 1915, he wasn't feeling well. And then here's a quote from a letter that Hardy wrote to the famous Swedish mathematician Mikael Gleffler, and you will see here that Ramanujan evidently was very seriously ill by this time. So the last 2 years in England were spent in sanitarium and nursing homes. It was thought that he had tuberculosis, but that diagnosis seems to be incorrect. A British physician, many years later, took all the symptoms that he could find from writings of others and concluded Ramanujan died of hepatic amoebiasis. This is an amoebic infection of the liver if dysentery is not treated properly. And apparently he had 2 bouts of dysentery before he actually went to England. So this physician, Dr. Young, convinced me this is actually how Ramanujan died. He said that if the diagnosis was properly made, he actually could have been saved. There were medicines available for recovery from dysentery. So as I indicated earlier, Ramanujan was elected as a Fellow of the Royal Society. These people are those that were in the Royal Society at that time. I put these 3 in italics because they actually weren't present for the voting. And you will notice the names of Hobson and Baker. These are the people who didn't bother to write Ramanujan after he wrote them. So Ramanujan returned to India in March of 1919, just after World War I ended. But unfortunately, his health did not improve, and he died on April 22nd, 1920, at the age of 32. So it was thought that his published papers and notebooks could be published all together. This didn't happen until 1927, when his published papers were collected together, but not his notebooks. The London Mathematical Society was in poor financial condition at the time, and so they did not publish the notebooks. So I mentioned that the notebooks are at the University of Madras, so you might guess, well, maybe they were sent to Hardy for publication. That's not quite correct. What happened was that a person at the library at the University of Madras copied the notebooks. That is, copied every page of the notebooks, and this copy was sent to Hardy in 1924. So those of you who might complain that your photocopy machine is slow, just remember that this copy was made by hand and obviously took a little bit more than a few minutes you would have on the copy machine. And one of the editors of the collected papers was B.M. Wilson. So here is the title page from the collected papers. And this is unusual for one reason. Does anyone see why this is an unusual title page? In fact, I don't know of any others containing this unusual characteristic. Anyone see any strange thing about this? Well, you will notice that B.M. Wilson's name is in larger print than the other 2 names, Hardy and P.V. Seshu Iyer, who was Ramanujan's teacher in the 1 year that he had at the Government College of Kumbakonam. So Hardy said that really Wilson did all the work in getting the papers together for publication. So evidently Hardy felt, well, he should be emphasized more than the other 2 of us as editors of Ramanujan's collected papers. So the notebooks began to be edited by Wilson and G.N. Watson in about 1928. So Wilson worked on this project for about 5 years, but unfortunately he incurred an infection in a hospital and died from the infection. And Watson worked on the notebooks for about 10 years and wrote about 30 papers arising from Ramanujan's notebooks. So when we say edit the notebooks, we mean trying to prove all the results in the notebooks, if they are indeed haven't been proved before. Yeah. So let me now tell you about my interest in the notebooks. I should mention one more thing before I say that. The notebooks were not published until 1957, when the Tata Institute of Fundamental Research in Bombay published a photocopy of the notebooks. Yeah. So as Atul mentioned, I was a graduate student at the University of Wisconsin, and in the second semester of my third year, I took a course from Rod Smart in modular forms. This was actually the first course in number theory that I ever took. So I liked this course very much, so I actually asked Rod Smart to be my advisor. And then in the first semester of my fourth year there, I took a course from Marvin Knopp on modular forms and applications to number theory. So this was the first time I ever heard of Ramanujan. Knopp in his course proved the general congruences for the partition function modulo any power of 5 and any power of 7. And I think he also stated, but did not prove, this famous asymptotic formula for the partition function that Ramanujan and Hardy derived. So this was very important because they formulated what is called the circle method, and this has been used countless times in analytic number theory since then. So Knopp was a student of Paul Bateman at the University of Illinois, and I will come back to him in just a minute or so. So another person who was influential on my work was Richard Ascii. I actually didn't take any courses from him, but he supported my work for almost 50 years. Unfortunately, he passed away just 3 weeks ago today. Okay, and as Atul mentioned, my first job was at the University of Glasgow, and my mentor there was Robert Rankin. So Rankin was actually the last Ph.D. student of Hardy. So he was always very much interested in Ramanujan's work, and I remember that one day in his office we talked about Ramanujan. So in particular, he told me about Ramanujan's notebooks, and this was the first time I had ever heard of these notebooks. And he said that he had the Tata Institute's publication in his office, and he offered to loan them to me. And in one of the most unwise decisions I ever made, I told him I wasn't interested at all in getting a copy or borrowing his notebooks. So in February then of February of 1967, I got a letter from Paul Bateman at the University of Illinois offering me an assistant professorship. It was a huge surprise because I only applied at the University of Illinois because Marvin Knopp said I should apply at the University of Illinois. I, as Atul mentioned, went to a small college, and I really wanted to return to a small college to teach for the rest of my career. So I hadn't really decided on a particular small college, so I accepted Bateman's offer to come to the University of Illinois. So as Atul mentioned, I never got to a small college. I stayed at Illinois for 52 years. So this is a photograph of Bateman. So in my second or third year at the University of Illinois, he asked me to referee 2 papers by Grosswald. So being head of the department, he got lots of duties assigned to him, so he was evidently asked to referee these papers, so he just gave them to me to referee. Well, in these two papers, Emil Grosswald proved some formulas from the notebooks. So here's a photograph of Grosswald. And I didn't really think much more about this until I was, well, let me just give you one formula from the notebooks. So this is a famous formula of Ramanujan. It's a formula involving the Riemann zeta function at odd positive integers 2n plus 1. So Ramanujan says if alpha and beta are positive integers such that alpha beta is pi squared, then we have this particular formula. So the B2K here are, these are Bernoulli numbers, they're rational numbers. Now, so Ramanujan has this symmetric hypothesis, and he liked to state his formulas or theorems evincing the best symmetry possible. Now, if you take alpha and beta both to be pi and replace n by 2n plus 1, then you get this identity. This actually is this special case is due to the Czech mathematician Dirac in 1901. So I've always liked this identity because it says here that zeta 4n plus 3 is a rational multiple of pi to the 4n plus 3 plus a very rapidly convergent series. Now zeta of 2n is a rational multiple of pi to the 2n. So here we don't quite make it. In other words, we got this rational multiple of times pi to the 4n plus 3, but we have this sort of error term. So I like to say that zeta 4n plus 3 is almost, this is not very mathematical, of course, almost a multiple of pi to the 4n plus 3. So these are from chapter 14 in Ramanujan's second notebook. And here is the page from the second notebook in which they appear. Okay, and this is the Tata Institute's publication of the notebooks. So I actually took this picture at home a little less than a year ago. I put a tapestry of, that I got in one of my trips to India as background here. So I didn't really do much after I refereed these papers of Grosswald, but in my sabbatical year, first sabbatical year at the Institute for Advanced Study in Princeton, in February of '74, I was working on generalized Eisenstein series, and I saw that all of these formulas that Grosswald had proved, I could prove using my formulas. So this is very exciting for me. And so I went to the Princeton University Library and checked out the Tata Institute's publication of the notebooks. So I found a few more formulas I could prove, but a few thousand others that I could not prove. So when I got home after the year ended at the Institute, one of the first things I did was to send a letter to the Tata Institute to send me a copy of the notebooks. It only costs $25, including shipping. It's a tremendous deal, over 3,000 theorems for $25. You just can't beat that. Yeah. So. The notebooks were republished on the 125th anniversary of Ramanujan's birth, and this is the new edition of the notebooks. It's easier to read than the old edition, but the old edition actually you can read fairly well. So I didn't really do too much in the next few years, but in May of 1977, after the semester ended at the University of Illinois, I said to myself, let's try to prove everything in chapter 14 of the second notebook. So I just did this as a personal challenge, and I chose this chapter because the formulas that Grosswald and I had proved earlier are from this chapter, so I had a head start on chapter 14. So I worked on this chapter containing 87 results altogether for a little over a year. And then in the fall of 1978, George Andrews visited at the University of Illinois, and he told me that when he discovered Ramanujan's lost notebook, about which I will tell you in maybe 5 or 10 minutes, he saw that the efforts that Watson and Wilson had made to edit the earlier notebooks had been preserved at Trinity College Library at Cambridge. So I wrote for a copy of these, thinking, well, if I had their notes, I could then edit further chapters. Okay, so to make a long story short, it took me a little over 20 years then, with the help not only of Watson and Wilson's notes, but several of my graduate students. And then, as Atul mentioned, I published then 5 volumes then on Ramanujan's notebooks. So let me just say a few words about what's in the notebooks. So there are a lot of results in what are called Q series. So Q series have in their sum ends frequently products of this type. So 1 minus a, 1 minus aq, up to 1 minus aq to the n minus 1. And if q is less than 1, then we can define aq infinity as the limit of aq sub n. So theta functions are part of the theory of Q series. So Ramanujan developed the theory of theta functions, not only the classical theory, but lots of new results as well. So he defined a theta function, f of a, b, in a way in which is not the classical way at all. But he chose this way because it evinces symmetry in the definition. So this product here is called the Jacobi triple product identity. And the 3 most useful special cases are these. So this is when A and B are both Q, then A is Q and B is Q cubed. It looks like I have a misprint here, but what I did is to fold up the negative index terms with the positive ones. And f of minus Q in his notation is f of minus Q squared. This is actually what's called the Pentagonal number theorem. So Ramanujan actually never used this notation. He would always just write out the first few terms of an infinite product, and also for series, he would never use the summation sign. He would just write out a few terms of the sum. And then he also worked on elliptic functions, which are closely allied with theta functions. So I'll just briefly tell you what an elliptic function is. So k of k is what's called an elliptic integral of the first kind. And this k here is called the modulus. It's between 0 and 1. And then the complementary modulus is k prime, the square root of 1 minus k squared. Okay, I won't say anything about this. This is a hypergeometric function. And actually, Ramanujan used that representation rather than the integral representation. Okay, so this definition probably won't make sense to you, but it's important for the next theorems of Ramanujan that I will tell you. So we have 4 different elliptic integrals associated with k, the complementary modulus of k, another modulus L, and then its complementary modulus. So we assume we have this identity holding for some positive integer n. Then what's called a modular equation of degree n, it's a relation between k and L, or in Ramanujan's notation alpha and beta, which is induced by this equality. So Ramanujan loved modular equations. In his notebooks, he has between 1 and 200 modular equations. So one of the reasons I think he liked them is because they are very symmetric in alpha and beta. So this is one of 15 modular equations of degree 3 that he derived. He had 15 modular equations of degree 5, and then 13 of degree 7. So he had lots of modular equations in his notebooks. So let me just summarize some of the things in the notebooks. He has a lot of infinite series identities, and I gave you one earlier involving the Riemann zeta function. A lot of results on theta functions and elliptic functions. I just briefly mentioned one hypergeometric series. This is a very classical type of series, and Ramanujan not only derived all the classical results, but many, many new results as well. And then I mentioned Q series, and then a special kind of Q series called basic hypergeometric series, and then it's not surprising in view of the fact that Ramanujan discovered many results in number theory in England, that there is a lot of number theory in the notebooks. Okay, so now let me tell you about the lost notebook. So I am going to reinterpret this passage through long lapse of time. Okay, so this is the time from Ramanujan's death to the discovery of the lost notebook. This knowledge was lost. In other words, the lost notebook. Yeah, having trouble with my area. But now, as you are devoted to truth, so that's George Andrews, I will reveal the supreme secret, the lost notebook. Yeah. So this was discovered by George Andrews in the spring of 1976. Lucy Slater, who was a professor in London and Cambridge, said that Andrews might find it profitable to look through the papers of G.N. Watson. And I should also mention, these are his daughters. This is Amy and this is Katie. So while looking through these papers of Watson, he found a sheaf of papers in Ramanujan's handwriting. And he immediately recognized this was Ramanujan's work. Not only was it Ramanujan's work, it was from the last year of his life. Because in the last year of Ramanujan's life, he wrote Hardy just once, and in this letter, he told about his new discovery, Mach theta functions. Andrews had actually written his thesis on some of Ramanujan's work, and in particular, Mach theta functions. So he immediately recognized this 77-page manuscript as from Ramanujan's last year. Yeah. So I'll give you a couple copies of a couple pages. This is one page from the lost notebook. So as you can see, this page is very hard to read. The pages that Andrews found were on all kinds of paper, and this piece of paper was obviously a piece of parchment paper, a very thin piece of paper. So what we're seeing here are two sides. In other words, when it was photographed, both sides of the piece of paper were photographed. So let me just say a few words about topics, and then I will go on with the history of the lost notebook. So in the lost notebook, there are even more results on Q series. So these are related to hypergeometric series, so let me just briefly indicate how they might be related. So what we're going to do is replace A by Q to the A. And we're going to let Q tend to 1 after we divide this by 1 minus Q to the n. So I take this quotient and I write it in terms of n quotients like this. And then we apply L'Hopital's rule and let Q tend to 1. Okay, so then we get what is called a shifted factorial or a rising factorial, and these are what appear in hypergeometric functions. So often a theorem in Q series has an analog in ordinary hypergeometric functions, but and conversely, but it's often very hard to find what this analog is. So this is an analog of the binomial theorem. It's called the Q Binomial Theorem. And if you replace A by Q to the A, as we did in the previous slide, and let Q tend to 1, you actually see that you get a version of the binomial theorem. There are a lot of results on theta functions, as I indicated, and then in particular, what are called false theta functions. False theta functions are theta functions, but you change the sign of infinitely many terms. So this was what we called psi of Q earlier, but without the minus 1 to the n. And the partial theta function is like a theta function, but you eliminate an infinite number of terms, usually those from minus infinity to 0. Here is an identity involving a partial theta function from the lost notebook. Okay, now let me discuss Ramanujan's last letter to Hardy, in which he introduces his new discovery, Mach theta functions. So I won't go through everything here, but what Ramanujan is doing is taking this Q series, which is actually the reciprocal of QQ sub infinity. And he looks at what happens as Q tends to 1. So at Q tends to 1, there's no convergence. So he says this is the main term, and this little o of 1 means that the remainder goes to 0 as we tend to 1. Okay, and then he says, suppose, so if we have a behavior like this, is it always going to be connected with a theta function? And he says here, not necessarily so. When it does not, he calls it a Mach theta function. So then he gives an example of a Mach theta function. So it's this series now. He looks at what happens as Q tends to 1. Then he remarks, it's inconceivable that a single theta function could be found to cut out the singularities of this function. This F has nothing to do with the previous F. I'm just quoting from Ramanujan's last letter to Hardy. And then he says, this is what we call then a Mach theta function. He never really proves this, that this isn't involving a theta function. So the Mach theta functions have been one of his greatest discoveries. In the last decade or two, they have been developed and by lots of mathematicians. And there is a variant called Mach modular forms, and these have appeared in physics, in particular string theory and black holes. And there are lots of applications of Mach theta functions. So this is one of the reasons I talked about these, because of their prevalence in research, and not only mathematics, but in physics and other areas today. Ramanujan extends the definition of a q of n to negative integers by this quotient here. And then let me quote one of the famous results of Ramanujan called his 1 psi 1 summation. This looks very complicated because there are 8 products on the right-hand side. So now this is involving negative indexed a sub n's or b sub n's as well. So this is a very useful theorem. Ramanujan derived lots of results, we think, from this theorem. There are a lot of results in Eisenstein series in the Lost Notebook. So the Lost Notebook was published in 1988 on the centenary of Ramanujan's birth. So not only was the Lost Notebook published, but there were lots of other manuscripts or partial manuscripts that were found at Trinity College Library, and also some at the Oxford University Library. So all these partial manuscripts and notes that Ramanujan had were published with the Lost Notebook. So the publication is called the Lost Notebook and other unpublished papers. Now, in some of them, we actually do not have the original manuscripts. So what Watson did was to copy some of the manuscripts. So all we have actually are Watson's copies of these manuscripts here. Some of them are extremely important. So in particular, there are 40 identities for what are called the Rogers-Ramanujan functions, which are very prominent in number theory. And perhaps the most important involves the partition function and one of Ramanujan's most famous function called the Ramanujan tau function. And Ramanujan wrote a very influential paper when he was in England on highly composite numbers, and he did some more work on highly composite numbers. So the question is, how did this Lost Notebook get into the library at Trinity College, Cambridge? Well, we think we can trace it back. So in 1923, the University of Madras Library sent to Hardy a package of Ramanujan's manuscripts. Unfortunately, we do not know what was in this package. The University of Madras didn't make a list, and Hardy never made a list as well. The University of Madras said to Hardy, just please return them at your convenience. Hardy never returned them to the University of Madras. So we think that late in Hardy's life, he gave them to Watson. So we think Hardy died in 1947, and we think he didn't give them to Watson until the late 1930s. And one of the reasons is that Watson wrote a paper on Mach theta functions in 1936, and he said, well, it's surprising that Ramanujan didn't discover these Mach theta functions. Well, if he had this manuscript from the lost notebook, he would have seen, indeed, that Ramanujan did discover these Mach theta functions. So probably sometime between the late 1930s and when Hardy died in 1947, he passed this material on to Watson. Now, Watson was professor at the University of Birmingham for many years, and he died in 1965. And after he died, he was paid a visit to his widow. His widow was paid a visit by Robert Rankin, whom I mentioned earlier. Now, Rankin had actually succeeded Watson as Mason Professor of Mathematics at the University of Birmingham. But when the professorship opened at the University of Glasgow, since he was a loyal Scotsman, he took the professorship at the University of Glasgow. So in the conversations that he had with Mrs. Watson, they discussed, what are we going to do with all these papers that Watson left behind in his attic floor office? And they agreed that what Rankin should do was that he should sort through all these papers, and those worth preserving be sent to Trinity College Library. Watson had always been fond of Trinity College, so this is why this library was chosen. So over a period of 3 or 4 years, Rankin would take trips to Birmingham and sort through these papers. And in fact, in my year at the University of Glasgow, that was in the midst of this time when he was sorting through the papers. So I now wonder, did he say something about papers of Ramanujan in the office when I talked to him that one day? And I really regret that I don't remember very much about that conversation, other than he offered me to borrow the earlier notebooks from him. So we think this is how the lost notebook and these other unpublished manuscripts got to Trinity College Library. In particular, Rankin kept notes of when he sent certain things, and these were sent in 1968 to the library at Trinity College. So there they remained for about 7.5 years before then Andrews rediscovered them. So Watson called this paper The Final Problem, and he borrowed it, the title, from a famous story of Sherlock Holmes. So Sir Arthur Conan Doyle wrote 24 short stories about Sherlock Holmes, and this is actually the last one that he wrote. Moreover, Sherlock Holmes' famous sidekick was Dr. Watson. So here is another reason why G.N. Watson borrowed this final problem from Sherlock Holmes' book. So at the meeting of the Royal Society 1 year ago to celebrate the 100th anniversary of Ramanujan's election, my wife and I went to the British Library, and Ken Ono and his wife went to the, so I went to the library, and he went to the museum. So he saw that, in fact, the manuscript of the final problem was on display. So you probably can't read that, but I'm diverting from mathematics for a minute to tell you what that says there. Professor James Moriarty, the Napoleon of crime. He is Napoleon of crime, Watson. He is the organizer of half that is evil and of nearly all that is undetected in this great city. That's London. He is a genius, a philosopher, an abstract thinker. He has a brain of the first order. He sits motionless like a spider in the center of its web. But that web has 1,000 radiations, and he knows very well every quiver of each of them. He does little himself, he only plans. So I hope that gives you some motivation to read about Sherlock Holmes. Okay, now I have actually taken another problem of Ramanujan and called it the final problem. So as George Andrews and I were going through the Lost Notebook over several years, and it took us a little over 20 years to actually finish our work, there was one problem actually that remained that we hadn't proved. And it's this problem that we hadn't proved, but we now have proved. So I'm running out of time, so I won't say too much about the problem. It's connected with a very famous unsolved problem that goes back to the 19th century in Dirac. So his divisor problem is this. We let d of n be the number of positive divisors of n. Okay, and then we'll take the sum of d of n less than or equal to x. So the prime on the summation indicates that if n is actually an integer x, we count only half of the terms. So Dirac showed that the main terms in estimating this are given right here. This 1/4 only appears because in analytic examinations, it pops up. So you really should ignore it. So gamma here is what's called Euler's constant. So the Dirac divisor problem asks for the growth of this error term as x tends to infinity. And Dirac showed that it's big O of square root x as x tends to infinity. So this means that if there exists a constant, positive constant, say c, such that if x is greater than c, then the error, if x is large enough, then the error term is less than the constant times x to the 1/2. But the actual order or magnitude of the error term is unknown. So that's the unsolved problem. You could think of this problem in another way. If you take a divisor of n, and then just let n be j times the divisor d, you can actually then identify every pair of divisors, j and d, with a lattice point, dj, in the plane. And they're under a hyperbola in the first quadrant. Now, unfortunately, my notation here is not very good because I've used x to be the upper index of my sum, whereas usually we would say that the hyperbola is xy equals a. So Dirac's divisor problem is equivalent to the problem of estimating the number of lattice points under a certain hyperbola. Okay, you could think of this in another way. So again, d of x, our summatory function, is you count 1 for every product of divisors dj equals n. So if we sum on j first, then the sum on j is just the greatest integer function, x over d. So we have this way of actually writing this sum of d of n. Okay, so this is what Dirac did. He said, let's count the divisors or lattice points in this strip, and count them in this strip. But we've counted these in this square twice, so we have to subtract them off. So just using this idea, this is how he got the main term, which I gave you just a minute or so ago. Okay, I'll skip this, but this is a classic formula derived by Voronoi in 1903, which is used to discuss the error term. So the delta of x that I gave you, the error term, is replaced by an infinite series, and I didn't go into this. These are what are Bessel functions here. Okay, so now let me give you Ramanujan's formula from a one-page manuscript published with the Lost Notebook. So he lets f of x be this. This is really equivalent to putting a prime on the sum. And this is his formula. Okay, it may not look interesting to you, but it's very interesting to many mathematicians who have worked on the Dirichlet divisor problem. So if I let theta be 0 here, I will actually get the representation for d of x as the sum of square brackets x over n. These are the same Bessel functions that appeared in the previous identity. And that previous identity has been used many times to whittle down the order of magnitude of the error term. In fact, is the main, this identity that I gave on the previous slide is the main thing which is used in the study. But now here we have an extra parameter, theta. In an analytic number theory, if we can introduce another parameter, it gives us more tools to work with. So I think that Ramanujan devised this formula with this extra parameter to work on the Dirichlet divisor problem. But I've never been able to figure out what his thinking was as to how he would ever use this to attack the Dirichlet divisor problem. So I've been thinking about this for 7 or 8 years, and I've gotten nowhere as to thinking about how Ramanujan would have used this formula. So let me just make a few comments. The sum on the left is actually a finite sum, and when theta equals 0, you actually get the sum d of x for the Dirichlet divisor problem. So my colleagues and I first proved this theorem with the order of summation reversed, but we had to make an assumption that we had convergence for one value of theta. So this work was done with my former student Sun Kim and my colleague Alexander Zarescu. And we did numerical work on the series that I just gave you, or the identity, and for a while we actually thought it was false because the series converged very slowly. Okay, well, we should never say Ramanujan was wrong. Indeed, the result is correct. Yeah. So we have now proved this last identity. So we is actually Junxian Li, Zarescu, and myself. So this is the final problem for Andrews and myself, the last identity in the lost notebook and other unpublished papers that was proved. So let me just end with a few questions. So Janaki, Ramanujan's widow, told me that when her husband returned from England, he had a whole trunk full of papers. So we don't have any of these papers from the trunk full. So this is a very, very sad thing to relate. Some of the papers or Ramanujan's work in England has not come down to us. And in fact, in my lecture tomorrow, I'll give some examples of results that appeared in Hardy's papers, but did not appear anywhere else. And also there are results in Ramanujan's letters to Hardy from nursing homes that only appear in these letters and not in his notebooks or his published papers. One page of Ramanujan's first letter to Hardy is actually lost. And a portion of Ramanujan's last letter to Hardy has also been lost. The original copy of this very important manuscript on the partition and tau functions has been lost. But we do have Watson's copy, so we hope that Watson covered everything, but we don't really know for sure. And as I said earlier, we don't really know the content of these papers that were shipped by the University of Madras to Hardy in 1923. It's really unfortunate that a list of these papers was not made. So in conclusion, if we're not for Robert Rankin, his visit to Mrs. Watson, we would not have the lost notebook either. So we're very fortunate that he went to see Mrs. Watson after her husband, G.N. Watson, passed away. So although everything has been proved, we don't know anything about a lot of Ramanujan's proofs. We still try to work to see how Ramanujan might have proved things so that we can understand his theorems much better than we do. So I don't plan to stop working on Ramanujan's work. So thank you very much for coming to my lecture.
Thank you, Professor. Thank you very much for this informative and interesting lecture. We have time for some questions. If anyone has any questions to ask. Yeah. Do we have a mic?